This is our final lecture on the crucial tests of Einstein's theory of gravity. You know, Einstein's theory of gravity is a relativistic theory, and before it, we have Newtonian theory of gravity, which is a classical theory. And our aim of this series of lectures is to test the validity of Einstein's theory of gravity on the experimental basis, which is called its crucial test. And in this regard, you have seen earlier my two lectures for the experimental test of Einstein's theory of gravity. And in those two lectures, we have discussed, first of all, the advance of perihelions of the planets, and in the second lecture you have seen a very important phenomena, that is bending of light rays in gravitational field. In fact, the classical Newtonian theory of gravity is not able to explain these facts, but Einstein theory successfully explains it, and in experiment such phenomenon is observed, and therefore these are called the experimental test or the crucial test of Einstein theory of gravity. The final proof or final experimental test, you can say, which we will learn today, this is regarding the gravitational redshift of spectral lines. In fact, again, the Newtonian theory is not successful in explaining this phenomenon. In other words, you can say that Newtonian theory of gravity does not account any redshift of spectral lines. Okay? But at the same time, you will see that Einstein's relativistic theory of gravity successfully explains this experimentally observed phenomenon. Okay? So the basic aim of our this present lecture, which will be a very short lecture, is to explain how Einstein's theory is successful in explaining the gravitational redshift of spectral lines. Okay? And so after this lecture, there will be a completion of our lecture on crucial test of general relativity or Einstein's theory of gravity. Okay. So now let us see how we can explain the gravitational redshift of spectral lines on the basis of Einstein's theory of gravity. Okay. This Einstein theory of relativity accounts numerically for the gravitational redshift or not. We will test it. Okay. In fact, finally, we will see that this theory is very successful in accounting the observed phenomenon of redshift of spectral lines emitted by an atom situated in a gravitational field. Okay. And for explaining this, let us consider there is a number of identical or similar atoms, and they are vibrating at different points in a gravitational field. We consider it. Okay. And we also assume that there is an atom which is stationary or which is at rest at a particular moment in our coordinate system, which will be just a spherical polar coordinate system. And in this coordinate system, the coordinates are r, theta, phi and t. So what we have assumed? We have assumed that among those vibrating atoms, there is an atom which is at rest in this coordinate system r, theta, phi and t. Okay. Now, starting from the Schwarzschild metric or Schwarzschild line element, which we have learnt in my previous videos, we will actually explain this fact very easily. So now let us see, you have learnt earlier what is this social metric or social line element due to a gravitating mass, let us say m, which is a very large mass, okay, that is like mass of sun or mass of moon and so on, okay. And you have learnt that this line element or social line element is given as ds square equal to minus 1 minus 2m over r whole to the power minus 1 dr square minus r square d theta square minus r square sin square theta d phi square and plus 1 minus 2m over r times dt square. This is the general expression for the social metric or social line element due to a mass m which produces the gravitational field. Okay. But as you have assumed there is an atom which is stationary, if the atom is stationary, its space coordinate will not change. So in this very condition, if the particle's position is fixed, it means this r, theta and phi are fixed. These are not changing. And if r, theta and phi are constant, these are not varying with time, then what will be dr, d theta and d phi? Since these are actually the elementary change in r, theta and phi, since r, theta and phi are constant, so these will be equal to 0. So if you want to write the expression for this social line element or social metric for the stationary atom or atom at rest, then what will be the expression? You can see easily from this equation that the first three terms in RHS will become 0 because the first three terms contains dr, d theta and d phi. Okay. So for the stationary atom, this line element ds square is simply given as 1 minus 2m over r times dt square. Okay. Now actually we have to compare the frequency or the wavelength of light emitted by the atom when it is in a gravity free space and it is observed by an observer. Okay. So if you talk about the part of a space which is free from any gravitational effect, or you can say that we are talking about a region of a space which is free from gravitation. Actually in that condition, you know, this ds is equal to dt, and therefore in this condition ds naught square will be equal to dt naught square. Actually here the subscript this 0 or naught represents the proper value of the time interval. Okay. So in a gravitation free part of the space, the metric becomes ds naught square equal to dt naught square. Okay. Because if you talk about the gravity free space, it means you are considering that there is no gravitating mass which produces the gravitational field, and in that very condition this m will be 0, and if m is 0, then ds square will be simply equal to dt square. But we are talking about the gravitation free part of a space, so we denote it by ds naught and dt naught. Okay. But you also know that this metric ds is invariant under the arbitrary coordinate transformation, and therefore we can write this dt naught square equal to 1 minus 2m over r times dt square. Okay. You can write it, and from here you can easily write this dt naught will be equal to 1 minus 2m over r whole to the power half times dt. Now see, This factor 1 minus 2m over r whole to the power half, this is a number smaller than 1. Okay, and when you multiply this dt by a number less than 1, you get dt naught. So definitely this dt naught is less than dt. Okay, it is clear from this equation. This is just like a time dilation. Okay, now what this dt naught less than dt refers, actually this result implies that a periodic phenomenon in the gravitational field of a heavy mass will appear to an observer outside the field as slowed down. It becomes slower. And this actually causes the red shift for the spectral line of light emitted by an atom situated in a gravitational field when this light is observed in a gravitation free part of the space. But how you can say this this result actually leads the red shift of a spectral line? For this, as you know, this time interval may be any time interval. Now we consider that this dt naught is the measure of the proper periodic time. This is the proper period of the vibration of the atom. Okay, and dt is observed or coordinate periodic time. Then, as you know, the time period is just reciprocal of frequency. You have learnt in elementary physics, if t is time period and nu is frequency, then t is equal to 1 over nu. So dt naught by dt, this will be just reciprocal of the frequencies. When time period is dt naught, frequency is nu naught. This is proper frequency. And when time period is dt, then frequency is nu. Since time period is reciprocal or inversely proportional to frequency, so this ratio dt naught by dt will be equal to inverse of nu naught by nu, that is, it will be equal to nu over nu naught. Okay, nu over nu naught. But let us see from this equation 4, what is this dt naught by dt? You can see this will be simply equal to 1 minus 2m over r whole to the power half. Okay, whole to the power half. So instead of this dt naught by dt from this equation 4, you may write 1 minus 2m over r whole to the power half. And therefore you can equate this nu over nu naught to this number. Okay, so I have written, you can see this nu over nu naught is equal to this much. Now let us expand the RHS by binomial expansion in first approximation. Since here this 2m over r, this is much smaller than 1. So by binomial expansion, you know, when there is 1 minus x to the power n, then this is almost equal to 1 minus nx if x is much smaller than 1. So this is called actually first approximation. So under first approximation, this will be 1 minus 2m over 2r. 2 will cancel out. So this is simply 1 minus m over r. This result has been obtained on the basis of binomial expansion up to first approximation. Okay. Now let us bring this 1 in LHS. So this will be nu over nu naught minus 1, and that is equal to minus m over r. And this is nu minus nu naught over nu naught equal to this much. Now you can see nu is the observed frequency and nu naught is the proper frequency or actual frequency, or nu is also called apparent frequency. Apparent frequency minus actual frequency, this is called shift in frequency or change in frequency. that shift in frequency has been denoted by the symbol delta nu. So delta nu is what? This is shift in frequency or change in frequency. And therefore our result is delta nu by nu naught equal to this much, or this shift in frequency will be equal to minus m over r times the actual frequency nu naught. So this is the expression for the shift in frequency. You can see here there is a minus sign in this expression. This negative sign implies that this nu is less than nu naught. It means the observed frequency will be smaller than the actual frequency. And you know, in electromagnetic spectrum, towards the red end of the spectrum, the frequency is smaller. In visible light, the smallest frequency is of red light. So you can say that this result shows that there will be a decrease in frequency, okay, of light as it leaves the gravitational field, and when it is received in a gravitation free space, there will be a decrease in frequency. And as you are saying that there is a decrease in frequency, it means you are tending towards the end of the spectrum where frequency is shorter, and that end is called red end, and this is called red shift. So I have mentioned, you can see this means there is a shift towards the shorter frequency side of the spectrum, and this is known as red shift of the spectral lines. Okay. Now you know, if lambda is the wavelength of the light, nu is its frequency, and c is its speed, then c is equal to nu times lambda, or you can say nu is equal to c by lambda. Okay, and therefore this d nu will be equal to minus c over lambda square times d lambda. Okay, you can see this minus sign actually refers what? When frequency will decrease, there will be an increase in wavelength, because nu is inversely proportional to lambda. Therefore, if you are talking about this delta nu, which is change in frequency, and nu naught, which is actual frequency, that will correspond a change in wavelength with negative sign. So you can say that this delta nu by nu naught is equal to minus delta lambda by lambda naught. And therefore, in this equation, that is equation A1, instead of this delta nu by nu naught, you can write what? Minus delta lambda by lambda naught. Minus minus in both sides will cancel out, and therefore our result is delta lambda by lambda naught equal to m over r. Okay, or this delta lambda will be equal to m over r times lambda naught. This is actually the shift in wavelength, which is actually positive. If shift in wavelength is positive, it means lambda, which is observed wavelength, that is greater than the actual wavelength, okay, lambda naught. So there will be an increase in wavelength. It is obvious, when there will be decrease in frequency corresponds increase in wavelength. So you can say there will be a shift of a spectral line towards the longer wavelength side, and longer wavelength side means red end side. Okay, this is actually called therefore it is called the red shift. Okay, now you know, if these equations A1 and A2 will be written in SI unit or MKS unit, then you know this small m is given by Gm divided by c square. In fact, in relativistic unit, you take G equal to M equal to C and all these equal to 1. In gravitational unit, as a relativistic unit, we consider it. But if we talk about the SI unit or MKS unit, then this small m is equal to Gm over C square, where this capital G is universal gravitational constant, C is speed of light. Okay. So in this case, if your aim is to write down these expressions in SI unit, then expression for delta nu will be minus Gm over C square times R times nu naught. And delta lambda, this will be equal to Gm over C square R into lambda naught. So these are the result predicted by Einstein's theory for the shift in frequency or shift in wavelength of the light emitted by a vibrating atom in a gravitational field. Okay. Now it is seen in experiment that the value predicted by this theory defined in equation A1 dash or A2 dash agrees within the observation of experimental error with these results. This has been tested actually for the gravitational field of the sun, and when we test these results for the gravitational field of the sun, it is found that these shifts which has been predicted by Einstein's theory uh, is in accordance with our experimental result. Okay, so we can say that Einstein's theory explains the experimentally observed phenomenon of gravitational redshift of spectral lines. Okay, so this is also an experimental proof, or this result, this explanation actually uh, validate the Einstein's theory of gravity. So in this way, we have completed in 3 lectures the experimental proof or experimental test, or you can say crucial test of Einstein's theory of gravity. Okay, and I hope after completion of these 3 lectures, your concept regarding this crucial test is very clear. Okay, thank you very much.